Alright, hello and welcome to geometry class. Let's talk about triangle congruence by side, 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 and side, angle, side. First of all, let me just point out that that doesn't say side, 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 and that doesn't say side, angle, side. It's just 3 S's and SAS. When we talk about these congruence statements, and lots of things in mathematics, of course, we like to abbreviate things and sort of make them a little bit shorter. So when we talk about side, 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 that's how we read this, side, side, side. And the S's just stand for side. These S's also stand for side, and that one stands for angle at A. So side, 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 and side, angle, side. You may remember from a previous lesson we said that if the 3 corresponding sides of 2 triangles are congruent, and the 3 corresponding angles of 2 triangles are congruent, that is 6 pieces of information. If the 3 sides and the 3 angles are congruent, then we have congruent triangles. So we needed this much. I needed to know my sides were congruent, and my angles. And with that much information, we could determine congruence. Then we said at some point by the third angle theorem that we could actually do with slightly less than that, just 5 pieces of information. So we went from needing side, 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 angle, 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 to simply side, 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 angle, angle. And so we went from 6 pieces of information to 5 by the third angle theorem. The question that we continue to wrestle with is, well, can we do with less information? Can I get there with even less? And the answer to that question is yes. It turns out that there are 2 new rules we need to talk about, side, 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 and side, angle, side, that will also carry the day. Let's look at those. Here's the side, side, side triangle postulate. It says if the 3 sides of one triangle are congruent to the 3 sides of another triangle, then the 2 triangles are congruent. Okay? In other words, I can do with just these 3 pieces of information. If I know they have the same 3 sides, that is 3 congruent sides, then the triangles have to be congruent. I'll show you that there's an activity you can do to sort of make sense out of this. If you can just find 3 objects of varying lengths. Here I have a pencil, a marker, and a Post-it note. And the question for us is, if we use particular aspects of these objects to represent fixed lengths, for instance, the length of the marker and the length of the pencil, and I'll use the length of one side of this Post-it note. The question is, how many different triangles can we make? Well, if I put vertex to vertex, that is endpoint to endpoint on these lines, and I form a triangle like this, I think you'll find, if you do this carefully, that there's only one triangle you can make. Whether I turn it around, rotate it sideways, switch these positions around to somewhere else, my triangles will be congruent. Now, even if I flip the marker around, it's not going to change the nature of my triangle. Same thing with the pencil or the Post-it. It's not going to change it because the endpoint, of course, is symmetric itself. Now, the marker is not symmetric, but the line that it represents, that is the side that it represents, or line segment, rather, is symmetric. I'd encourage you to do that at home. Get 3 different objects. See how many different triangles you can make. See if a friend can make a different triangle. You'll find that there's only one triangle that can be made from 3 segments of fixed length. So that holds out true. How do we sort of observe this in geometry? Where do we go with this? Well, the question for us, the question we're trying to answer a lot of times is, are 2 triangles congruent? Are they congruent? And so we look, if we want to apply the side, side, side rule, we just look for congruent sides. So suppose I have this information. It's kind of straightforward. I ask the question, are these 2 triangles congruent? The answer is yes. Question, how do you know? Well, side, side, side. Side, 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 triangle congruence postulate. All right, suppose I didn't have congruence marks. Suppose instead of congruence marks, we knew the lengths of these sides. We have 7 units, 4 units, and 6 units. And we ask the question, are they congruent? Yes. How do you know? Side, side, side. Okay. Let's look at one slightly less obvious problem. Suppose we had triangles like this. Further suppose we're told that those are congruent. That side measures 7, and that side measures 7. And the question for us now is, are these 2 triangles congruent? Are these 2 triangles congruent? The answer to the question is yes. How do we know? Well, to answer the question, we begin to think about the rules. Well, do we know 5 pieces of information, or 6? Do we know that all 3 sides are congruent, and all 3 angles, corresponding angles and sides? The answer is no, I don't know anything about the angles in this problem. Okay, what about side, side, side? Do I know that they're congruent by side, side, side? Well, I've got one side congruent here. I've got 2 sides congruent here, the 7 and the 7. And then we have the third side here. We have a question about that third side. Do we know if those are congruent? The answer to the question is yes. By the reflexive property. We go ahead and put names on this. Let's call this A, B, C, D. Again, we know that AB is congruent to AD. Those are segments. We know that segment BC is congruent to segment DC. CD wouldn't be wrong, but it's probably not ideal. CD. And then the question is, what about segment CA? Is that congruent to segment CA? Well, yes, by the reflexive property. Segment CA is congruent to segment CA. So then the question is, how do we write the congruent statement? Which triangle is congruent to which triangle? Triangle ABC is congruent to triangle ADC. Notice the order in which we name the points. It's important that we name corresponding parts in the same order. All right, the next rule we need to talk about is the side-angle-side triangle congruence postulate. Side-angle-side. It says if two sides in the included angle of one triangle are congruent to two sides in the included angle of another triangle, then the two triangles are congruent. When you talk about this word included, you figure out what that means. Included is one of these words in geometry that is always used in a particular context. It doesn't have any meaning by itself. You'll never be walking down the road and see an included angle. It doesn't exist. You'll never see one in isolation. So what do we mean? When we talk about a triangle, for instance, triangle ABC, the included angle is the angle that's between two specified sides. So if I'm talking about side AB and side BC, in the context of that discussion, angle B is the included angle. Okay? If instead I talk about side AC and side BC, then angle C is the included angle. And I think you can see if I talk about side AC and side AB, then angle A. Notice that if you're just given the names of two sides, for instance, side AB and side BC, you don't need a diagram to figure out what the included angle is. All you need to do is look for the common vertex. Here, we have AB and BC. B is the included angle. AC and BC, C is the included angle. AB and AC, A is the included angle. So again, an included angle is the angle between two particular sides. Let's just look at a quick activity to see if this one makes sense, this postulate. Remember, postulates are generally not proven, but they should be somewhat intuitive. They should be sort of obvious to us. Suppose we had a fixed angle. Here, I've just drawn one on this Post-it note. And I handed you two sides of fixed length. And the question is, how many different triangles can I form with this angle and these two sides? That's the question. Well, we don't have many choices here. We can put the pencil here and the marker here, and that gives us a triangle. Or we can put the pencil here and the marker down here, and that gives us a triangle. But I think you'll see that no matter how we do that, we could always flip the triangle or rearrange the triangle so that in every circumstance we'd be dealing with exactly the same triangle. I'd encourage you to do that at home. Even if you just have some paper available, you can just draw an angle on one of them and then fold up some paper so you have some line segments and see how many different triangles you can make. I think you'll find you can only make one triangle. Okay. All right, let's look at a couple examples of how this works in practice. Let's just look at this before we go any further. That's the question, are these two triangles congruent? The answer here is I don't have a clue. Because I don't know anything about any of their sides or any of their angles. So I'm not in a position to make that determination. Suppose I had the following information instead. Suppose we asked whether these two triangles are congruent. Well, we don't know anything about these two angles or this side, but we do know something about these two sides in this triangle and this angle, and these two sides over here in this angle. And so we can try to figure out, do we have a postulate or a rule that we've learned so far that will tell us whether these two triangles are congruent? And if you try to apply the side, 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 I think you see pretty quickly that it fails because we don't know the length of side AB, we don't know the length of side ZY, and so side, side, side won't work for us. What about side, angle, side? Can I get there by side, angle, side? I look for two sides that are congruent, 8, 12, 8, 12, so I've got the sides, and then an included angle. So in this case, the included angle here is angle C, and over here the included angle is angle X. And you see here that angle C is included between AC and CB, and angle x is included between yx and zx, so they are the included angles. So by side angle side, those two triangles are congruent. Let's just take the further step of writing the congruent statement so we can be sure what that should look like. When I begin, I really can't mess this up. Say that triangle ABC is congruent. I can name this any way I want, but once I name this order, I'm fixed on my order over here. Triangle ABC, I have to name it in corresponding parts. So A corresponds to Y, and B corresponds to Z, and C corresponds to X. Triangle ABC is congruent to triangle YZX. Notice the name. The last thing we need to look at is determining congruence in the coordinate plane. How do we figure out in the coordinate plane if two triangles, for instance, are congruent? Well, since we have this new rule, side, 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 we can just run the distance formula on each of the 6 sides, in this case 3 sides on triangle ABC and 3 sides on triangle DEF. We can run the distance formula on all 6 of the sides and then compare corresponding sides and see if they have the exact same distance or same length. If they do, then the sides are congruent, and therefore by side, 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 the triangles are congruent. So the first thing we need to do is just run the distance formula on all 6 of the sides. Okay, I've gone ahead and run the distance formula on each of the segments. Segment AB, distance from A to B is square root of 41, so side AB has length 41, square root of 41 units. Segment BC, square root of 50, segment CA, square root of 13, and over here you can see that corresponding segments all match up and are congruent. So segment DE is congruent here to segment AB, and square root of 50 for EF, BC, and square root of 13 for FD to CA. Notice one thing, I did not find these values, I didn't put them in a calculator because I'm not actually interested in knowing what the values are. At this point, all I really want to know is, are they congruent? And based on the analysis with the distance formula, we can safely conclude that they are in fact congruent. And so now we know by side, 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 since this is congruent to this, and this to this, and that to that, we can conclude that the triangle is congruent. That is how we determine congruence in the coordinate plane. If you have any questions, please send me an email.